So a while back, we took a look at different kinds of triangles, and we learned that isosceles triangles are triangles that have two congruent sides. So I've got an isosceles triangle right here. You can see that the two sides of this triangle are marked congruent. There are specific names for different parts of this isosceles triangle. For instance, the sides that are congruent are called the legs. So in this particular triangle right here, this side would be considered a leg, and this side over here is a leg. The other side is called the base. So this side down here is called the base of this isosceles triangle. Now, I want you to realize that the base will not always be at the bottom of the triangle. For instance, if I look at this other isosceles triangle down here, I have my legs as segment AB and segment AC, then segment BC right here would be considered the base, even though it's not on the bottom of this triangle. So base is just the side that's not congruent to anything in an isosceles triangle. The angles that are at the base, there's two of them. There's an angle at each end of the base. Each one of those is called a base angle. So that's a base angle right here, and this angle right here. These two angles, they are referred to as the base angles. So this is a base angle over here. Lastly, the angle that's formed by the legs. So I forgot to put a blank for this one, but this angle right up here, it's formed where the legs meet together right here. The angle that's formed by the legs, that is called the vertex angle. So if I could find some space, maybe right here. This is called the vertex angle of my isosceles triangle. Now, all those terms are going to be important for you to know and remember, because we're going to talk about some of those things as we learn some special theorems that apply only to isosceles triangles. So first of all, down here, Theorem 4-1, it says if two sides of a triangle are congruent, then the angles opposite them are congruent. So in other words, if I have my isosceles triangle down here, where segment AB is congruent to segment AC. So if in this picture, segment AC is congruent to segment AB, then according to this theorem, the angle that's opposite AC, so if we go from AC and we go straight across the middle, that would be angle B, it's going to be congruent to the angle that would be across from segment AB. So if I go straight across the middle of my triangle, I'd be looking at angle C there. So with segment AC congruent to segment AB, it makes the angles opposite them congruent. Angle B and angle C are congruent. That's Theorem 4-1. So if we wanted to try and apply that theorem to a picture like this, we have an isosceles triangle, right? And in example 1, we are told that the measure of angle 1 is 140 degrees. So let's just write that in there right there. 140 degrees for angle 1. What's the measure of angle 2, angle 3, and angle 4? Well, first of all, I might want to remember that according to Theorem 4-1, in this picture, if this side and this side are congruent, it would mean that angle 3 would be the same as angle 4, because they're opposite these congruent sides. So I can keep that in mind, that angle 3 and angle 4 have to be the same. And I know that angles 1 and 2 would add up to 180. So I know that the measure of angle 1 plus the measure of angle 2 should equal 180. Well, I know now that angle 1 is 140. So 140 plus, we'll call that x, needs to equal 180. So that would mean that x would equal 180 minus 140, which is 40. So x, or the measure of angle 1, is equal to 40. Now I also know that if I take the measure of, that measure of angle 1, this would be the measure of angle 2. If I take the measure of angle 2 plus measure of angle 2 plus the measure of angle 3 plus the measure of angle 4, I know that that should all add up to 180, because those are the interior angles of my triangle. I now know that angle 2 is a 40-degree angle, and I know that these are both the same. So if I put an x in, I shouldn't use x, I already used x. Let's put a y in for angle 3 and a y in for angle 4. I know that those three things add up to 180. So that would mean that 40 plus 2y equals 180. I'll come over here, and if I subtract 40 from both sides, that would mean that 2y equals 140. And if I divide both sides by 2, I would know that y equals 70. So the measure of angle 3 and the measure of angle 4 both equal 70 degrees. So angle 2 in this example in part A was 40 degrees, and angles 3 and 4 were both 70. In example B, it says, what if angle 4 is 65 degrees? So right here, I have 65 degrees. Now let's get rid of this 140 because that no longer applies to this example. So I have angle 4 is 65. What are angles 1, 2, and 3? Well, first of all, I know that angle 3, the measure of angle 3, is equal to the measure of angle 4, so that's equal to 65. So I got a 65 degree angle right here for angle 3. I also should remember that since angle 1 is an exterior angle of this triangle, the measure of angle 1 will be equal to the measure of angle 3 plus the measure of angle 4. So that would be equal to 65 plus 65. So that's going to be 130 degrees. So now I know that this is 130 degrees. And I know that 1 and 2 add up to 180. So the measure of angle 2 would be 180 minus the measure of angle 1, which is 130. So it's going to be 50. So angles 3 and 4 are both 65. Angle 1 is 130, and angle 2 is 50. Now in theorem 4-2, we have we have basically the converse of the one that we just talked about, theorem 4-1. In this case, if we have two angles that are congruent in a triangle, like if angle B is congruent to angle C, then I know that the sides opposite them will be congruent. So the side that's opposite angle B is segment AC. Segment AC is guaranteed to be congruent to the side that's opposite angle C, which is segment AB. So AC is congruent to AB in this example. So if I look at example 2 down here, it says find the value of x. Segment RT's length is 4x plus 4, and segment ST has a length of 32. But angle R and angle S are congruent. So if angle R is congruent to angle S, then I know that RT should be congruent to ST. Or another way to say that is that the length of RT should equal the length of ST. So that would mean that 4x plus 4 should equal 32. Subtract 4 from both sides, 4x equals 28, and divide both sides by 4 would give me x equals 7. So the value of x in example 2 is 7. Now we have a few corollaries that we're going to look at that kind of can be derived from this idea that if sides of a triangle are congruent, then the angles opposite them are congruent. So if I look at an equilateral triangle, right, if AC is congruent to BC and is also congruent to AB, so if all three of these sides are congruent, well, that would mean that the angle across from AC, which is angle B, would be congruent to the angle across from BC, which is angle A, and the angle that's across from AB would be congruent to angle A, so that would be angle C is congruent to angle A, and that means that angle B and angle A and angle C, they're all congruent to each other. And we've actually already discussed this in class before, but this is where it gets formally introduced. Now, what would be the measure of each of those, right? If they're all the same, if I called them all z, so if that's z degrees, and this is z degrees, and this is z degrees, I know that all three of those z's need to add up to 180, which means that 3 z's make 180, which means that each z must be 60. And we've actually talked about that already again, so this is more or less review. Now, the next one, it says that the bisector of the vertex angle of an isosceles triangle is perpendicular to the base of the triangle at its midpoint. That's a little bit wordy, but here's what we have. We have this triangle here where segment WU is congruent to segment WS. In other words, it's an isosceles triangle. And this vertex angle W, that's where the legs, that's the vertex where the legs meet. That angle has been bisected. You can see here that angle UWT is congruent to angle SWT, or in other words, the vertex angle has been bisected. Then, oops, that's not where that's supposed to go. Let me back this up a little bit. Sorry, I think in this example right here, what I was supposed to say is that angle UWT is congruent to angle SWT. Sorry for the confusion there. Then, so if this angle has been bisected, sorry about that, if this angle has been bisected, this vertex angle of this isosceles triangle, then this point right here is the midpoint of the base, or in other words, we can say that segment UT would be congruent to segment ST, and this is a right angle, and this is a right angle because it says that this bisector will be perpendicular to the base. So I could say that the measure of angle UTW and the measure of angle STW will both equal 90. They will both be right angles. Lastly, we have a corollary that says, and I think I messed my numbering up there. Sorry, guys. You may have noticed that my corollary 1 is repeated twice. I don't know why that is. Sorry. If a triangle is equiangular, then it's going to be equilateral. So in this picture, if angle D is congruent to angle E and is congruent to angle F, then the side that's across from angle D will be congruent to the side that's across from angle E. So EF will be congruent to DF. But then that side that's across from angle E will also be congruent to the side that's across from angle F. So DF will be congruent to DE, or in other words, this is an equilateral triangle. And again, we've kind of talked about that. So that's maybe nothing brand new. The last thing that we're going to look at is a real quick proof involving these ideas that we've talked about in this video. I have this picture here with a triangle ABC, and I'm given that angle 1 is congruent to angle 2. So, and I'm supposed to prove that, and I'll do this in orange with my little question marks, I'm supposed to prove that segment AB is congruent to segment BC. So how am I going to do that? Well, first of all, if I know that angle 1 is congruent to angle 2 because it's given, I also know then that angle 3 is congruent to angle 1 and angle 4 is congruent to angle 2, right? Those are congruent. Those pairs of angles are congruent because vertical angles are congruent. And that means that if angle 3 is congruent to 1 and 1 is congruent to 2, then angle 3 is congruent to 2 by the transitive property. Transitive property, right? 3 is congruent to 1 and 1 is congruent to 2 makes 3 congruent to 2. But then if 3 is congruent to 2 and 4 is congruent to 2, then that means angle 3 is congruent to angle 4, also by the transitive property. So also by the transitive property, right? 3 is congruent to 2, but 2 is congruent to 4, makes 3 congruent to 4. And now if angles 3 and 4 are congruent, then I can say that segment AB must be congruent to segment BC. And my reason, I could put the theorem down here, the theorem number. This would be theorem 4-2. Well, if I don't remember theorem 4-2, if I don't remember that number, I can say that if two angles of a triangle are congruent, then the opposite sides are congruent. And that is theorem 4-2 if you're going to try and remember those numbers. But I don't remember the numbers very well usually, so I just try and put an abbreviation of what the actual theorem says. So there you have a quick little proof using some of the things we've learned so far, the vertical angles being congruent, transitive property, and then this theorem 4-2 from this video. All right, so I will see you next time. And there should be a video that you'll be watching that is going to do some proofs using this information that we just learned in this. So check that out. All right, talk to you later.